The Cayley-Hamilton theorem says every square matrix A of size n satisfies its own characteristic equation. In symbols, if the characteristic polynomial of A is p of lambda equals determinant of lambda I sub n minus a equals lambda to the n plus c sub n minus 1 lambda to the n minus 1 plus plus c sub 1 lambda plus c sub 0. Then replacing the scalar lambda by the matrix itself gives p of a equals a to the n plus c sub n minus 1 a to the n minus 1 plus plus c sub 1 a plus c sub 0 I sub n equals 0 sub n by n. A simple way to see why this works is to use the adjugate matrix. For any matrix M, we have the identity M adjugate of M equals determinant of M I sub n. Take M equals lambda I sub n minus a. The left-hand side is a matrix whose entries are polynomials in lambda. Expanding the product and then setting lambda equals a, which is allowed because the equality holds for every scalar lambda, turns the factor lambda I sub n minus a into the 0 matrix, leaving only the term p of a I sub n equals 0. Hence p of a equals 0. More rigorous proofs use induction on n or the Jordan normal form, but the adjugate argument captures the core idea in a few lines. The theorem works for any field real numbers, complex numbers, or even modular arithmetic, which makes it a universal tool in engineering mathematics. Explanation: construction of the characteristic polynomial and evaluation at the matrix itself. To build the characteristic polynomial, follow these steps. Step 1. Write lambda I sub n minus a. Think of lambda as a placeholder that we will later replace with the matrix. Step 2. Compute the determinant of that expression. The determinant collapses the matrix into a single variable polynomial. For a 2 by 2 matrix, A equals a matrix with entries A, B, C, D. P of lambda equals determinant of a matrix with entries lambda minus a negative B, negative C, lambda minus D. This expands to lambda squared minus open parenthesis a plus D close parenthesis, lambda plus open parenthesis a D minus B C close parenthesis. Step 3. The coefficients C sub I that appear are functions of the trace, sum of principal minors, and so on. They are like the DNA of the matrix. Once the polynomial is ready, the Cayley-Hamilton theorem tells us to plug the matrix back in. P of a equals a to the n plus c sub n minus 1 times a to the n minus 1 plus plus c sub 1 times a plus c sub 0 times I sub n equals 0. In practice, this means you can replace any power a to the n or higher by a linear combination of lower powers. This replacement is the engine that drives later applications, similar to how a recipe lets you trade a hard to make ingredient for a mixture of easier ones. A real-world analogy: imagine a machine, the matrix that processes a signal. The characteristic polynomial is the machine's frequency response. Plugging the machine into its own response tells you that after a certain number of cycles, the output repeats a predictable pattern, the 0 matrix. Explanation: determination of matrix powers a to the k using the Cayley-Hamilton relation. Because p of a equals 0, any power a to the k with k greater than or equal to n can be reduced. Take the example of a 3 by 3 matrix with characteristic polynomial p of lambda equals lambda cubed minus 6 lambda squared plus 11 lambda minus 6. Cayley-Hamilton gives a cubed minus 6 a squared plus 11 a minus 6 I equals 0. Therefore, a cubed equals 6 a squared minus 11 a plus 6i. Now to find a to the 5s. A to the 4 equals a times a cubed equals a open parenthesis 6 a squared minus 11 a plus 6 I close parenthesis equals 6 a cubed minus 11 a squared plus 6 a. Replace a cubed again. A to the 4 equals 6 open parenthesis 6 a squared minus 11 a plus 6 I close parenthesis minus 11 a squared plus 6a equals open parenthesis 36 minus 11 close parenthesis a squared plus open parenthesis negative 66 plus 6 close parenthesis a plus 36i equals 25 a squared minus 60a plus 36i. Then a to the 5 equals a times a to the 4 equals a open parenthesis 25 a squared minus 60a plus 36 I close parenthesis equals 25 a cubed minus 60 a squared plus 36a. Substitute a cubed one more time. A to the 5 equals 25 open parenthesis 6 a squared minus 11 a plus 6 I close parenthesis minus 60. A squared plus 36a equals open parenthesis 150 minus 60 close parenthesis. A squared plus open parenthesis negative 275 plus 36 close parenthesis. A plus 150, I equals 90 a squared minus 239 a plus 150i. The key point colon, you never need to multiply matrices more than n minus 1 times. This saves a lot of computation, just like using a shortcut on a GPS avoids unnecessary turns. In engineering, such reductions are used to compute powers of the state transition matrix in discrete time control systems, where a to the k describes the system after k steps. If A is invertible, the constant term C0 in its characteristic polynomial is open parenthesis negative 1 to the n power close parenthesis det a, and therefore non-zero. Starting from a to the n plus cn minus 1 a to the n minus 1 plus dot 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 plus c1 a plus c0 I equals 0. Move the constant term to the other side and factor out an a. A left parenthesis a to the n minus 1 plus cn minus 1 a to the n minus 2 plus dot 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 plus c1 I right parenthesis equals negative c0 I. Multiplying both sides by negative 1 over c0 gives a inverse equals negative 1 over c0 times left parenthesis a to the n minus 1 plus c n minus 1 a to the n minus 2 plus dot 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 plus c1 I right parenthesis. Thus the inverse is expressed as a polynomial in of degree n minus 1. For a 2 by 2 matrix, this reproduces the familiar formula. If p of lambda equals lambda squared minus open parenthesis a plus d close parenthesis, lambda plus open parenthesis a d minus bc close parenthesis, then c0 equals a d minus bc equals det a, and a inverse equals 1 over det a times left parenthesis a minus open parenthesis a plus d close parenthesis I right parenthesis. In practice, engineers use this to avoid Gaussian elimination when the matrix size is small, but the entries are symbolic, for example transfer function matrices. It also shows why a non-invertible matrix cannot satisfy a polynomial with a non-zero constant term. The constant term would force a division by 0. A physical analogy. Think of a gear system where the characteristic polynomial tells you how many rotations of one gear produce a full cycle. The inverse gear ratio, the backward motion, can be computed directly from the same polynomial without dismantling the whole mechanism. Many engineering problems need e to the at, the matrix exponential, for example, solving linear differential equations in control theory. The exponential can be written as a power series. E to the t equals I plus a t plus a squared t squared divided by 2 factorial plus a cubed t cubed divided by 3 factorial and so on. Because of Cayley-Hamilton, any power a to the k with k greater than or equal to n can be reduced to a combination of a through a to the n minus 1. Hence the infinite series collapses to a finite linear combination. E to the t equals alpha 0 of t times I plus alpha 1 of t times up to alpha n minus 1 of t times a to the n minus 1, where the scalar functions alpha I of t are determined by matching coefficients, often done by evaluating the series at the eigenvalues or by solving a small linear system. This is exactly what the Jordan form or Sylvester's formula does, but Cayley-Hamilton guarantees that a polynomial of degree n minus 1 is enough. Other analytic functions such as sine of a t, cosine of a t, or I minus a t inverse are handled in the same way. Expand in a series, truncate using the theorem, and collect terms. In electrical engineering, the response of an RLC circuit can be written as e to the t, where I encodes the circuit parameters. The theorem lets you write the response explicitly without infinite summation. A simple illustration. For a 2 by 2 matrix with characteristic polynomial lambda squared minus 3 lambda plus 2 equals 0, we have a squared equals 3a minus 2i. Then e to the t equals I plus a t plus 3a minus 2i t squared divided by 2 factorial plus 3a minus 2i a t cubed divided by 3 factorial and so on, which after collecting I in a terms gives e to the t equals 1 minus t plus t squared over 2 factorial minus I plus t plus 3t squared over 2 factorial plus a, and the series in parentheses are just elementary functions that can be summed. The characteristic polynomial p of lambda contains all eigenvalues including multiplicities. The minimal polynomial m of lambda is the monic polynomial of smallest degree such that m of a equals 0. Clearly m divides p because any polynomial that annihilates a must contain each eigenvalue factor at least once. If p of lambda has distinct linear factors, no repeated eigenvalues, then m of lambda equals p of lambda, and the matrix is automatically diagonalizable. If some eigenvalue repeats, diagonalizability depends on whether the geometric multiplicity, number of independent eigenvectors, equals the algebraic multiplicity, its exponent in P algebraically. This is equivalent to m of lambda having no repeated factors. That is, m of lambda must be a product of distinct linear terms. Thus, the presence of repeated factors in the minimal polynomial signals the need for Jordan blocks, non-diagonalizable parts. In engineering, diagonalizable matrices are preferred because they simplify dynamics. A system x dot equals a x decouples into independent scalar equations when a is diagonalizable. An easy way to test diagonalizability using Cayley-Hamilton. Compute p of a, which is 0, and factor p. If you can write a as a polynomial in itself with distinct linear factors, you can construct the projector matrices that separate the modes. Analogy: think of the characteristic polynomial as a recipe listing all ingredients' eigenvalues. The minimal polynomial is the shortest version of the recipe that still produces the same dish. If the short recipe repeats an ingredient, the dish will have a layered flavor Jordan block. If every ingredient appears only once, the flavors stay separate, diagonalizable. Explanation: solving systems of linear differential equations with constant coefficients using Cayley-Hamilton. Consider the system x dot equals ax where x of t is an n vector and it is constant. The solution is x of t equals e to the t times x of 0. Using Cayley-Hamilton, we replace the infinite series for e to the t by a finite combination of a to the n minus 1. E to the t equals sum from k equals 0 to n minus 1 of beta sub k of t times a to the k, where the scalar functions beta sub k of t are found by solving a small system derived from the differential equation itself, or by evaluating at the eigenvalues. Once the coefficients are known, the solution becomes a simple linear combination of known vectors. X of t equals open parenthesis beta 0 of t times I plus beta 1 of t times a plus plus beta n minus 1 of t times a to the n minus 1 close parenthesis times x of 0. For a 3×3 matrix with characteristic polynomial lambda cubed plus 2 lambda squared plus lambda minus 2, the relation a cubed equals -2 a squared minus a plus 2i lets you write any higher power in terms of a squared. Substituting into the series for e to the t yields a closed-form expression involving only exponentials of the eigenvalues. This technique is widely used in mechanical vibrations, mass spring damper systems, where the state matrix captures stiffness and damping. Engineers obtain the time response without diagonalizing the matrix. A real-world picture. Imagine a fleet of interconnected drones whose positions follow x dot equals ax. Cayley-Hamilton tells you that after a certain number of interaction rounds, the whole fleet's motion can be described by a handful of basic patterns, making prediction and control feasible. Suppose A equals a 3×3 matrix with first row 2, 1, 0, second row 0, 2, 1, third row 0, 0, 2. Its characteristic polynomial is lambda minus 2 cubed, which expands to lambda cubed minus 6 lambda squared plus 12 lambda minus 8. Cayley-Hamilton gives a cubed equals 6 a squared minus 12a plus 8i. Compute a to the 4th power as a times a cubed, and then a to the 5th as a times a to the 4th, repeatedly substituting the relation to keep powers less than or equal to 2. The final answer is a to the 5th equals 32, a squared minus 80a plus 64i. Take B equals a 2×2 matrix with first row 0, 1, second row minus 2 minus 3. Its characteristic polynomial is lambda squared plus 3 lambda plus 2. Compute b squared plus 3b plus 2i. B squared equals a 2×2 matrix with first row minus 2 minus 3, second row 6, 7. 3b equals a 2×2 matrix with first row 0, 3, second row minus 6 minus 9. 2i equals a 2×2 identity matrix with diagonal entries 2, 2. Adding gives the 0 matrix, confirming Cayley-Hamilton for this concrete case. Let C equals a 2×2 matrix with first row 4, 2, second row 1, 3. Its characteristic polynomial is lambda squared minus 7 lambda plus 10. Thus C0 equals 10 equals the determinant of C. From the theorem, C squared minus 7C plus 10 I equals 0, which implies C inverse equals 1/10 times open parenthesis C minus 7 I close parenthesis. Carrying out the arithmetic gives C inverse equals 1/10 times the matrix with first row 4 minus 7, 2. Second row 1, 3 minus 7, which evaluates to a matrix with first row minus 0.3, 0.2. Second row 0.1 minus 0.4. Which matches the result obtained by the ordinary formula C inverse equals 1 over the determinant C times the matrix with first row 3, minus 2. Second row minus 1, 4.